Now we are defining what is a complete space. To define a complete space, we need a metric space x comma t. X comma t is a metric space, and this metric space is said to be complete if first of all we need to have a metric space, and second is we need to have a Cauchy sequence. The second one is the Cauchy sequence, and the Cauchy sequence, if every Cauchy sequence in X converges to a point of X, every Cauchy sequence in X converges to a point of X. Okay, here X is actually a metric space. This is a metric space, and we will take a Cauchy sequence from this metric space, and that Cauchy sequence should converge to the point of X. This is the complete definition of a complete space. Once again, what should you have to complete the definition of complete spaces? The first is you must have a metric space x comma t, and there should be a Cauchy sequence in that metric space, and that Cauchy sequence should converge to the point of X, this X, to the point of X. This is the definition of a complete space. Now we are taking a theorem. So what is the statement of the theorem? The statement of this theorem is actually related to the complete space. So what is the statement? The statement is a subspace Y, a subspace Y of a complete metric space of a complete metric space of a complete metric space is complete if and only if Y is closed. This is a very important theorem in functional analysis or metric space. So it means that when we talk about if and only if, then the converse of this theorem exists. What is given before if and only if, and what is given after if and only if. Before only if and only if, Y of a complete metric space is complete, and we will prove that Y is closed. In the converse statement, we will take Y is closed, and we will prove that Y is a complete metric space. First of all, we are taking the first part of if and only if. What is the first part? The first part is a subspace Y of a complete metric space is complete. This is the first part. And what is the second part of if and only if? That is Y is closed. So we will take a subspace Y of a complete metric space is complete. This is given, and what we will prove that Y is closed. So let me start the proof of this theorem. Suppose that Y is a complete subspace. Y is a complete subspace. We are taking actually the first part of if and only if. Y is a complete subspace, then this means that we want to prove that Y is close. If y is a complete subspace, y is a complete subspace of X, then by the definition of complete subspace, y contains all its limit points. This implies that if y is a complete subspace, then this implies that y contains all of its limit point, all of its limit points. Okay, and let y be the limit point of y. Let y, small y, be the limit point of y. Capital Y, which is a subspace. Then for every open ball, then this means that there exists an open ball B whose center and radius is just like S, y and 1 over n, y and 1 over n. By the definition of a limit point, the intersection of this open ball with y should not be equal to empty set. So if it is not empty, then this means that there is a point, common point, and let that point is common, which is yn. So yn is actually the common point in between P y comma 1 over n and intersection with y. This is the common point. Then this means that the distance between yn and y should be less than 1 over n. So from this we can write the distance between yn and y should approach to 0 whenever 1 over n is approached to 0 as n approaches to infinity. So from here we can write that yn actually converge to y. Okay, since yn is convergent, if yn is convergent, being convergent the sequence, yn is a Cauchy sequence. If it is convergent, yn is convergent, then this is a Cauchy sequence in X. If it is a Cauchy sequence in X, therefore this is also Cauchy sequence in Y. And if converges to Y, yes, of course it is converges to Y. Since Y is complete, so Y belong to Y. Hence Y is closed. If it is complete, then this is closed. Hence Y is closed. and similarly the converse of this theorem. We will take the second part and prove the first part. I am over here not taking the second part. This is the assignment for you and hope you will do this.